You learned that pi equals 3.14159 ... A constant, universal, eternal. It shows up in circles, in waves, in quantum mechanics, basically everywhere. But what if I told you this version of pi only exists in a universe that doesn't exist? Not a philosophical trick, a mathematical and physical one. There are actually two types of pi, and most people have only ever heard of one. By the end of this video, the number 3.14159 will feel very different to you. Let's start with something that sounds almost too simple. What is a circle? In Euclidean geometry, a circle is the set of all points equidistant from a center. Beautiful definition, but notice the word all points. How many points are on that circle? Infinitely many. And every single one of them has 0 width, 0 height, 0 size. 0 size. Infinitely many of them. That is the foundation of classical geometry. Here is the question nobody asks in school. Does a point like that actually exist in nature? Let's try to find one. Let's zoom into matter, all the way down. Atoms. They have size, roughly 10 to the minus 10 meters, not points. Quarks inside protons. Still not points. Quantum uncertainty smears them out in space. And then we hit a wall, the Planck length, approximately 10 to the minus 35 meters. Below that, our physics, all of it, stops working. Space-time itself becomes undefined. Many approaches to quantum gravity, loop quantum gravity, causal set theory, propose the universe has a minimum length. Nobody has proven this, but let's follow it and see where it leads. If that's true, physical circles are not made of infinite zero-size points. They are polygons, with a very large but finite number of sides. And when you compute pi from a polygon with n sides, you get a formula that approaches 3.14159, but only reaches it when n is infinite. The mathematical pi, 3.14159, is the limit as n goes to infinity. But in physics, n cannot go to infinity. The universe runs out of small. So if that premise is right, physical pi is always slightly less than mathematical pi. Not because pi is wrong, but because a physical circle at that scale isn't a mathematical circle. It's a polygon. The gap is astronomically tiny at human scales, but it is real, and it has consequences. Now here is where it gets beautiful. What happens at the absolute smallest scale? Here is a constraint most people never think about. In a discrete universe, if lambda min is truly the smallest possible length, then any measurable distance must come out to a whole number of those steps. A circle has two measurable distances, its circumference and its diameter. For a physical circle to exist, both must be whole number multiples of lambda min, simultaneously. Which regular polygon satisfies both conditions at once? Let us run the elimination. Triangle, 3 sides, circumference 3 steps, whole number, good. But the diameter equals 2 divided by root 3. Root 3 is irrational. You cannot measure it with any whole number of minimum lengths. Triangle fails. Square, 4 steps around. Diameter is root 2 times lambda min. also irrational. Square fails. Pentagon, heptagon, octagon, all irrational diameters for the same reason. Now the hexagon, 6 steps around the circumference, and the diameter, center to opposite vertex, is exactly 2 steps. Circumference divided by diameter, 6/2. Exactly 3. This is not a coincidence. There is a theorem in mathematics, Niven's theorem, 1956, which proves that among all regular polygons, the hexagon is the only one whose perimeter-to-diameter ratio is rational. Every other polygon produces an irrational diameter. The hexagon is not a shape we chose. It is the only shape that is internally consistent in a discrete universe. And it gives us pi equals exactly 3. Let me put this precisely. Call the minimum length lambda min, the Planck length. For any physical circle of radius r, the number of discrete sides is this. And the physically measurable pi, the one a real ruler would give you, is this. Plug in r equals lambda min, n equals 6, and pi equals exactly 3. The hexagon. As r grows, n grows, and pi climbs, slowly, continuously, toward 3.14159. But it never reaches it, because no physical radius can be infinite. Let me give you some numbers to make this concrete. Planck scale, n equals 6, pi equals 3.000. Size of a proton, n is about 10 to the 20, and pi is already indistinguishable from 3.14159. At 1 centimeter, the difference between physical and mathematical pi is less than 10 to the minus 60. That is why we don't notice it in everyday life. But it is there. Now, why 6? Why does the minimum polygon have exactly 6 sides and not 5 or 7? Hexagons tile a flat plane perfectly, with 0 wasted space. No other shape does this as efficiently. Nature optimizes. At the smallest possible scale, the universe doesn't have room for geometric waste. So the geometry at the bottom of reality is hexagonal, and hexagons give pi equals 3. For now, let us summarize what we have established. Pi is a function of scale. At Planck scale, it equals 3. At large scales, it approaches 3.14159. This comes from one thing. Space has a minimum length. And that minimum forces the smallest circles to be hexagonal. None of this contradicts known physics. Every equation still works. We are just looking deeper. We are asking, where do the numbers in those equations come from? Let us name them clearly. 2 types of pi, 2 different contexts. Mathematical pi, pi sub infinity, lives in the Euclidean plane. It is a constant, 3.14159. It requires infinitely many zero-size points on its boundary, a magnificent abstraction. And it is incredibly useful. Every bridge, every GPS, every circuit board depends on it. It is not wrong. Physical pi, pi of r, is what any measuring instrument in the real universe would return. It depends on scale. It is always between 3 and pi infinity, and it is always slightly smaller. The Euclidean point, zero size, infinite precision, is the exact dividing line between these 2 worlds. Accept the zero size point as real, and you get pi infinity. But you also inherit the infinities that plague quantum physics. Reject it. Accept that the smallest thing has finite size, and those infinities vanish. The vacuum energy problem, the ultraviolet catastrophe. These are symptoms of forcing infinite precision into physics. The discreteness doesn't fix them by hand. The geometry simply doesn't allow them to exist. This is Zeno's paradox in disguise, by the way. To cross a room, Zeno says, first go halfway, then half of that, then half again, forever. Mathematics resolves this with convergent series. 1/2 plus 1/4 plus 1/8 equals 1. Beautiful, elegant. But that series has infinitely many terms. Does the universe perform infinitely many steps? In a discrete universe, no. There is a last step. The arrow completes its journey because space ends. Zeno's paradox is not really about motion. It is about whether infinity is physical or just mathematical. And the answer this framework gives us is, infinity is a tool, a magnificent tool, not a physical fact. Space has a smallest length. The mathematics we use to describe it can be infinite. They are different things. We have proven it. The minimum circle at the Planck scale is a hexagon. Circumference, 6 steps. Diameter, 2 steps. Pi, exactly 3. Not a choice, the only answer that is internally consistent in a discrete universe. But we live in 3 dimensions. And in 3 dimensions, the minimum discrete structure is not a circle. It is a sphere. Because a sphere, like a mathematical point, has no preferred direction. It looks the same from every angle. As soon as you ask the question, 2 principles emerge, and they point in different directions. The rationality principle, the one that forced the hexagon, applied to 3D gives the cuboctahedron. It is the unique polyhedron where the circumradius equals the edge length exactly. And when you look at it from above, along the 1, 1, 1 axis, you see the hexagon. The isotropy principle gives the icosahedron. It has the highest possible discrete symmetry, 120 symmetry operations, the closest solid to a sphere. But its circumradius involves the golden ratio phi, irrational. We have seen this before. In 2D, the pentagon was eliminated because its geometry involves root 5, forbidden at the Planck scale by Niven's theorem. The icosahedron is the 3D pentagon. Same golden ratio, same irrationality, 1 dimension higher. The ratio between the 2 answers is precisely related to the golden ratio phi. Phi is not decoration. It is the exact measure of the tension between rationality and isotropy in 3-dimensional space. And here is what makes this more than abstract. Icosahedral symmetry appears everywhere in nature. In viruses, in carbon-60 fullerenes, in some models of the proton. Because 5-fold symmetry is the most isotropic way to organize discrete structure in 3 dimensions. They may be echoes of the fundamental geometry of space. Which one is the minimum sphere? The rational one or the isotropic one? This depends on which principle is more fundamental at the Planck scale. And nobody knows. Look at what we've found. In 2D, the 2 principles agreed. Rationality and isotropy gave the same answer, the hexagon. That agreement was not obvious. It was a coincidence of dimension. In 3D, they diverge. And the golden ratio is the distance between the 2 answers. We came here asking about pi. We found that at the smallest scale, pi is forced to be exactly 3. and asking what happens one dimension up, we found not certainty, but a question. A beautiful, unresolved question. Whatever nature chose at the Planck scale, the hexagon is its shadow. And that shadow has a name. Pi equals 3.